Well, this is the de facto eclipse library. It's got everything to do with lunar cycles, eclipse cycles, great astrological years, solar and lunar intercedent cycles, the great history back all the way through to creation, and some interesting complicated math, a little bit of side notes, and a bunch of custom new animations. So I know it's going to be super long. This took probably more work than I've ever put into any video that I've ever put on the internet. So watch it, don't watch it. I don't know. Hopefully it'll be worth it. And yeah, take the time to sit this one through. I think it'll be worth it. Thanks. Let's touch real briefly on just the importance of solar and lunar calendars because they had different measures of time throughout history. Lunar cycle was popular for ancient Hebrews, etc. If you look through a little bit more closely, from the antediluvian, it was mostly lunar until for some reason they decided to go solar, which was a disaster for most people. Let's see here. The Babylonians, of course, had the ancient Saros, so they had at least an 18-year calendar based on a lunar cycle, you have to assume, since that's the year, how long a lunar cycle is. Chinese had the same as well. Essentially, everyone based their calendars on either the moon or the sun, and overwhelmingly was the moon. And nowadays, it's the sun or even the Julian calendar, which is a complete edition of all calendars. Right, so the basics, the sun and the moon, the basic celestial bodies we'll be talking about. Now, we know, ever since the times of Kepler and Newton and all them, that people have taken notice of the path and the travels of the celestial bodies in the heavens. And of course, we know that Kepler made observations, just observations, and then from those observations created laws, quote, which ended up being mathematical descriptions of the paths of the celestial objects. And then Newton came along and tried to insert mass as a dynamic cause in that same equation with some varying results. Let's not go into that crazily. However, there was a kinematic equivalence guised as a dynamic equivalence that later we can remove. But Newton came along and added to Kepler's laws of motion. And again, just motion. He looked at the sky, saw what they were doing, described it using math. Newton came along, did the same thing, inserted mass. We're not going to go over there. We can backwards derive that right out. But this is a good image to see the celestial bodies have a definite periodicity. Literally can be described as the time it takes to return, right? And they have an orbit, and that piece of that orbit is always the same. That's why they call it, yeah, the periodicity, right? So this description here would be applied to most celestial objects. This is important because we're going to go into how later on exclusivity for heliocentricity does not exist with predicting eclipses. They cannot do it without the geocentric position, no matter what they say, but we'll go into that in greater detail later. Just sticking with the basics some more, like I said, let's bounce from the equation of time and the eccentricity of the sun as a direct impact of the dance between the sun and the moon over the period of the ecliptic and the great astronomical year. It reminded me a great deal of the tides because they have a dynamic semi-diurnal oscillating tide, which again is directly based on the relationship of the sun and the moon's orbit and the intersections. They have these crazy tides that literally have to do a double diurnal oscillation with a wag front with a hula hooping thing. Anyway, the eccentricity between those two causes a lot of similar things. In this way, they use harmonic frequencies to predict tides. Again, very, very strange and cool. Here's a couple little looks at that, harmonic constituents, etc., and how they get tides to work. I wanted to go through what is an actual eclipse, right? Let's just go through the basics. Just real quick on the sun and the moon eccentricity. I said I remember the tides because the tides are a byproduct of also the sun and the moon's eccentricity. They say it's a gravitational influence. That's nonsense, of course. It is, however, an electromagnetic influence that the moon seems to have with the highest high tides and the lowest low tides by its phase. But let's just stick to the eccentricity. So like this is the effect of the eccentricity of the sun, or the obliquity, right? So this creates the equation of time, and I'm just pointing this out because the eccentricity of these two bodies creates an awful lot of dynamic systems in our realm. So essentially, for the tides, they do this intercession of let's see, they do hula hooping, right? So you have a semi-diurnal tide, which means it has super high highs and super low lows, and that's hula hooping around. And then the moon is also hula hooping around, so they have these two hula hooping orbits that intersect and leap. We'll get to that later, but for this purposes, the way that they predict tides and what they call tides is a frequency, because they use what's called harmonics, right? Harmonic constituents, and they literally have tidal frequencies, which are just a great example of the interaction and the intercedence of the sun and the moon on that wonderful scale. Right, so there's a couple of images showing that. And like I said, it just so happens that all of this is created by the eccentricity of the sun and the difference in the speed between the two celestial bodies. The proximity of the two is always what causes eclipses, whether you believe they're real or not real, physical, not physical, projected, there, not there, what have you. Their assumed apparent proximity is a catalyst for at least a solar eclipse. But we'll get into that in just a moment. Of the sun and the moon, right? Let's see if we still have this here. Step interval 1 hour. Yep, go. So essentially, we want to see why the sun and the moon intersect when they interact, right? And this would tell you the general speed of each. But of course, if you speed it up, you'll notice that it'll look like the sun will lap the moon. Here we go. Let's get that rolling, and we'll see the same thing, right? So we have the sun speed chasing the moon, it looks like, or is the moon chasing the sun? This is going to show the difference in the sun and the moon speed. So I sped it up till about here, and then I started, I think, changing the months faster. So you'd see which one was faster, right? So we have the moon is trailing the sun. We're moving the months. It's in May. We move to June. It's catching up. We move to July. It's catching up a little bit. We move to August. It's a little bit closer. September, October, November. It looks like the sun's not moving, but it's just an optical trick here. And as we get closer, is the sun going to lap the moon, or does the sun catch up? Does the moon catch up to the sun? Thing to say. Essentially, the speed difference between the two is the only thing that allows the interaction and the intercedence of their elliptical paths, right? So the only thing that would allow that is if they had a different speed. If they were the same speed, they would never meet. The same reason why solar time is 4 minutes different than sidereal time. And the difference between those two, of course, creates the equation of time. So just something to keep note of. All right, and again, just to get the idea of the difference between the speed of the sun and the speed of the moon, giving us not only the eclipse cycle, but day and night, seasons, all that good stuff. Let's see, we're a little bit faster. Let's do about this fast. There we go. So as it gets closer to the sun, it loses its energy. See the waning, let's call the new moon low energy and the full moon high energy, just because of the basis on luminosity. And let's just say that the further the moon is away from the sun, the brighter and more luminous it becomes. And the closer it gets to the sun, the less luminous and dimmer it becomes. So we can only have a solar eclipse when it's in new moon, meaning when it's either not there or almost invisible to see, right? That's weird. It's weird that that's the only time we can have a solar eclipse. The time when we can't actually see the moon, we know it's eclipsing the sun. Anyway, we'll come back to that. So again, this is the speed is coming back around. The sun's coming to the moon. They're going to intersect soon. And the second that the phase changes, like the new moon, that means it just passed the sun. Right? So it only gets into new moon with proximity to the sun. Do we think that's a coincidence? In any case, as far as the eclipse cycle works, what we're taking away from this is that the moon has to be in its new moon phase when it passes the ecliptic at this node, or no eclipse will happen. It has to be in the new moon phase. That's the only way a total solar eclipse can occur. As interesting as that is. Now, the smallest building block of the big celestial cycle is the lunar cycle. That is the basic building block, right? And this is what we're talking every month, the lunar cycle, the phasing it goes through, how long it takes for it to go through its circuit, essentially, right? And for this case, which is faster, the sun or the moon, the sun does appear a little bit faster, but we'll get to that in a little while. So it makes one complete circuit of the ecliptic in 365.24 days, essentially a little bit more than the sun, essentially meaning a little bit slower than the sun. But it always says that because the moon's orbit with respect to the sun has a mean duration, there'll always be at least one, maybe two solar eclipses during each 34-day interval when the sun passes through one of those nodes. So when they have to intersect, the moon will be in its proper phase, there will be an eclipse. This is calling the seasons of eclipses. This is when you're looking at the orbits in the periodicity, there'll be a specific time where it's more likely and a specific time where it's not. 6 months in, 6 months out, essentially. That's all that's referring to. And again, the lunar cycle, 29.53 days, also known as a synodic month. That is very important. We'll get to that in a little while. But just to visualize what the sun is doing compared to what the moon is doing compared to the sun, let's take a look at this video here. It shows you, I think, the nice analemma and what the pathway would do and how it looks. There we go. You see how it has 3 days when it's not there, literally isn't visible, so its analemma will always show that gap. I found that super interesting because that gap wanders. It's not fixed and static because it's always in a different spot, right? As those missing periods travels the length of its analemma, this is the result. Right, not bad. It's very different than the sun's. It shows you that there's a different path that it takes just slightly, right? So we do know between the two speeds of the two that the sun is a little bit faster than the moon. That will play an important role as we get to actually plotting and predicting eclipses. All right, and on to the phases of the moon, which everyone should be familiar with. We've all been told since we were kids what these were. Surprisingly, if you look for information on the internet, you will find overwhelmingly videos tailored to kids for this particular phenomenon. Not sure why that is, but there are many more kids-facing explanations of lunar phases than any adult explanation. Anyway, essentially we know that the moon goes from its new moon, right, all the way to its let's say waning or waxing crescent, to the first or third quarter, to the waxing or waning gibbous, and to the full moon, right? That's the usual progression of the moon. We can take a quick look over here. It says it begins with new moon, which means no moon, and then it appears larger until it reaches the full moon phase, and then it appears thinner like a waning crescent. It becomes the new moon. Now when they say appear, they mean optically only, of course. So new moon between Earth and the sun, only lit by light reflected from Earth. That is nonsense, of course, craziness. But we'll just go through with an animation, show you the animation of the heliocentric version of the phases of the moon. So we got the path of the moon here. We're going to start with the phase called the Aphelion, as it's furthest from the sun. It's the brightest. This is the full moon. You know, its distance from the sun is so large that it's not being interfered with, however. And we're going to rotate around as it's approaching the sun. It's, you know, losing luminosity, approaching a new moon. Can almost see it at the last crescent. And finally, right before it reaches the sun, or right before it gets close proximity, it goes almost totally dark new moon, and that's the perihelion, where it's closest to the sun. And then it just keeps going after that, and away we go, and it starts the beginning luminosity regaining, what you want to call it, and off to its next phase it goes. So the relationship we wanted to show here is that the moon is always in a new moon when it's near the sun in its proximity, and brightest when it's furthest away. So dimmest when it's near the sun, brightest when it's furthest away. Very important. And back to our database here, we're just going to take a quick look at the difference between the phases of the northern and southern hemisphere. Of course, in the south it looks upside down due to perspective. Don't be crazy. It's very easy to understand why that would be. Here's a good picture of what it would look like. Here, just, you know, what we just witnessed. Again, when it's closer to the sun, near and visible. Always weakest near the sun. Here's about evening sky, right? And then, of course, another look from the other side. It's always weakest when it's near the sun. That is the basic thing to take away from this. We got some basic lunar calendars when they do the complete phases by month for the whole year. And now, finally, we can get into eclipses. So the path of the sun and the moon and the interaction there within create sort of every system on Earth, right? Our concept of time is directly related to the sun, day and night cycle. The complicated geometry that results from their paths over the flat Earth and as they process it's simple as itself, but it ends up painting a pretty complicated design, right? And here's another image of what it would look, what the path of the sun and the moon technically do look like. We all know that, right? This is the sun, this is the moon. They do the same sort of orbiting path, and at sometimes they intersect. And at those times, they create what's known as a lunar ascending or descending node, right? So these are just intended to give us a guideline of how we know the sun and the moon move. And of course, that's not the actual way they move. Let's look at our model here and we'll get a really good, close, in-depth description of the lunar path and the solar path and how they intersect. All right, and what better than Shane's flat Earth model to get some visuals on the sun's ecliptic versus the moon's ecliptic and what those two would look like. I'm going to turn the camera off for now, but I'll pop on when we need to say something. Right, so in this program, the ecliptics function as a solid line geometrically. It's easier. That's not what I'm saying they're doing. I'm just saying for this model, this is good because we can see how they're different. You see how it's inclined above the Earth? From this top-down position, you can see it's a little bit more inclined. You can see that it kind of follows the same path of itself, but is, missing the moon, right? They're following a similar orbit, but different. Nice top-down view. Those other lines, of course, being the tropics and the equator. It's a nice view, from about 2/3 up. And again, that's the tilt of the ecliptic. You can see it's a little bit different. See how it's not perfectly flat and horizontal over the Earth? Nope, it's at a little bit of an incline. It's going to be very important when we're trying to predict the intersection of the sun and the moon. And that's moving the time of the year, so we can see the moon moving in conjunction with the sun. Notice it's above its little path right there. And again, this is just the geometries of the ecliptics of the sun and the moon. See how they're always interchanging and forming this kind of intersection point with sacred geometry? Those dots you see on the orbit, those are the nodes. They put 4 for equinox, or 2 for equinox, 2 for solstice, and 2 for lunar nodes. So this is by far the best representation of what we're talking about here with their paths, right? Or at least from a geocentric perspective in reality. So right there, they're intersecting, they're moving the paths, and you can see exactly how they interact. Or moreover, how frequently they should interact, right? And how frequently they don't. Geometries more. Notice how the nodes are traveling backwards, or they also appear to be. And there's the sun's on its ecliptic. Here comes the moon. So again, just whipping it around the ecliptic right there. They're very close. Sun and the moon are very close. They happen to be, but you see how they're still not going to hit? There's 3 dimensions to their intersection, right? They are on all, if it was a level plane and they were just orbiting, then their orbits would have to coincide. But because it's 3D, the orbits and the inclination has to coincide, which makes it much more difficult and much rarer. Here it is again. The whole view right over the Earth. Again, we have the sun and the moon at a tilt. There they go, doing their periodicity that they can never tire of, right? Over and over and over again. Again, this is a good pictorial representation of what we're talking about. First of all, that incline right there and how it's different than the moon's. Right, so yeah, right there. Right here is how we can see this beautifully. See how this is a slight incline? This is the path of the moon. This is a steeper incline, the path of the sun. Because they're intersecting, it's so much less likely for them to interact, right? Let's take a look here. And the top-down view again. Both ecliptics again. On this model, it does move them together when you go progressing the time forward, and you have to move the date to move the moon, but that's just an aspect of the simplification of the programming to make it possible to do this in the first place. It does a great job of these two things, though. That ecliptic right there is what we're talking about, and how it's inclined, even though when it moves, it's still inclined. You see how the moon has its own inclination as that goes around the Earth and completes their orbits. Yeah, doing a great job moving the eccentricities of their orbits. I think at the end we'll just have it play the whole little eclipse simulation sped up a little bit. Again, points out the ecliptic of the moon. It says that it extends further north than the sun. That's because it goes beyond the tropics, according to, we'll see, now it says that those dots are the intersection points. Now that is the moon's orbit. Again, I'm going to show the plot. Those knot is what it's calling, is the nodes. That's the nodes are going to move backwards. See how the sun's not really moving, but see how the node is moving? He's doing both right now. So the moon is going, the sun is coming around. We're going to line them up for an eclipse, right? So it's going to stop right there. And again, this shows how the nodes move. They are non-physical, places that they intersect at, but they're always in motion, and they're moving in the opposite motion from the sun and the moon, apparently. And they say that if they meet at a knot, an eclipse happens. Again, the moon has to be in new moon phase for an eclipse, usually. But it has to be in the proper phase, and if it's in the proper phase and it's at the node and the sun is near, an eclipse will occur. Absolutely. So here it is, right at the node, and there's the moon. Boy, that's a definite solar eclipse right there. Oh, there was one. How about that? How would that work for individual observers again? Oh, that's right. That's right. I remember now. The spherical limit of vision tied to 3959 derived from the limits of optics, of angular resolution, etc. We'll go into that later. So this is just a nice quick demonstration of what an eclipse would look like, assuming some things and ensuring simplicity, right? So it's approaching the person. It hasn't yet risen up. Now it rose, and there they are, and they're aligned right there as it passed, right there. Aligned and ready to go. Once they set, of course, not aligned anymore. But I think that was a pretty great demonstration of what we're talking about, and this is more importantly, the sun's ecliptic in relation to the moon's ecliptic and what those tilts mean. Just going to play a minute or so of this video. It is from a globularist, but he does a really good job of explaining how an eclipse repeats, and more importantly, how the graph of that eclipse differs from Saros to Saros.
Will this happen again? After an eclipse, the moon has drifted past the sun. In order to coincide again, the moon will have to complete a full lap around the sky. If we carefully measure the moon's speed, we can predict that this should take about 29.5 days. So we wait until 29.5 days have passed, and nothing happens. The moon missed somehow. A closer look at the moon's motion reveals why. In addition to its sideways travel, we can also make out a slight up and down motion. In order to cause an eclipse, the moon needs to be vertically aligned with the sun. It crosses this line once every 13.6 days, completing a full up and down cycle after 27.2 days. So let's start with an eclipse and follow the full motion of the moon. It completes an up and down cycle after 27.2 days. It reaches the sun after 29.5 days, but is now 2 days into its next up and down cycle, causing it to miss. If we follow the moon for another lap around the sky, we see that things get even worse. It completes its second up and down cycle after 54.4 days, but doesn't reach the sun for another 5 days after that, missing by an even wider margin. If we keep our attention on the sun, we'll see the moon fly by every 29.5 days. There are many close calls, but a total eclipse will not occur until the up and down cycle matches up with the around the sky cycle. They do eventually come back into sync after 6,585.3 days, or 18 years, 11 days, and 8 hours.
I'm going to go over these images a little bit. They are pretty much graphs of how close a particular transit or passing of the moon over the sun's ecliptic is to becoming an eclipse. Right in the middle would be a dead-on total eclipse if it was in the right phase for the moon. And any other one, if it's on the left and heading right, it will eventually, start over here, get more accurate, and then taper off. Or if it's on the right and then heading towards the center, that it will eventually be more accurate before being less accurate. And I believe that all of these are the same thing. Yeah, so for lunar, it's the same one. Depending on which one of these they hit, it will be how eclipsed the eclipse will be, or how the shadow will be hidden. But we'll definitely go over that shadow in more depth in a little bit. It is definitely not the shadow of Earth, of course, but we can also know how to use Besselian coefficients to correctly calculate and project it out from anywhere on the celestial sphere. And then here we have the annular one. It's the same thing. Pretty much the gradation chart for determining how much of any transit could be considered either one of these eclipses.
This family of repeating eclipses is known as a Saros cycle. This particular cycle is Saros number 145. Every eclipse belongs to a particular Saros, and there are currently 40 active Saros cycles, each generating its own sequence of eclipses on a repeating 18-year schedule. If you look at a map showing eclipse paths over a period of time, such as this one, which shows all of the total eclipses from 2001 to 2025, you can often spot pairs of eclipses that belong to the same Saros. Notice these two paths have a similar shape and are about a third of the way around the Earth from each other. If we check their dates, we see this one happened in 2003, and this one occurs 18 years later in 2021. These are two sequential eclipses from Saros 152. This path from 2001 is a close match to this path from 2019. These are eclipses from Saros 127. Finally, these S-shaped paths are 18 years apart, representing Saros 139. Although these paths are similar looking, they are not exactly the same. Eclipse paths in a Saros cycle gradually change shape over time. For instance, Saros 145 produced its first total eclipse on June 17, 1909, with a path that nearly crossed the North Pole. 18 years later, a slightly bigger path cut around the Arctic Ocean. Cycle after cycle, these sequential eclipses worked their way south, leading to the American eclipse of 2017. This Saros will continue producing eclipses for another 600 years. Its final total eclipse will be visible from Antarctica on September 9th, 2648.
All right, and the basics for a lunar eclipse, right? And we'll stick with the heliocentric explanation. When the Earth passes between the sun and the moon, causing the Earth's shadow to fall on the moon. The moon moves into Earth's shadow, leading to a dimming or darkening of the lunar surface. Now, that would be a neat explanation if it worked, right? Well, let's just take a look here. This is just a guide on how they would determine what type of lunar eclipse would it be, whether it be a total, partial, penumbral. And again, this is just a diagram of how close to the center is the moon to the sun when it goes over the ecliptic. And if it's off, then the next time, if it's progressing right, it'll be closer and closer and closer, etc., and vice versa. Here's another image. This is how they actually judge eclipses, how they're going to be when they do the calculations later, and they do the celestial sphere projection of the shadow umbra. So total lunar eclipse, right? It's the when they say the moon moves into the inner part of Earth's shadow or the umbra, and that it gets dimly lit, and that they have colors with shorter wavelengths, scatter easily, and then longer, like red and orange, don't. And that's what they say is happening here. They also say that it kicks up dust clouds that are always orange and reddish, and that's what obscures it. Anyway, another type of a lunar eclipse would be partial, where it's imperfect and it looks kind of like this, right? This would be a total, always looking red. This would be a partial, it's about that. And then penumbral happens all the time. You wouldn't even notice it. It's right here, right? Basic. Does anyone see a problem with this definition, right? It seems to be that if it's for a lunar eclipse, if the moon is passing between the sun and the earth, and the shadow's being cast, that shadow would have to maintain a specific distance, right? It would have to maintain a specific directionality to it. It couldn't say change directions or anything. Let's take a look at some of these examples here. But first, let's go to this video. We'll look in Stellarium for what a lunar eclipse should look like, right? Let's see here. Right, we'll find it. We'll mark it. Right, so what it is obscuring, it should come from that direction. Okay, there it is. All right. All right, so obscuring, occulting from the top because it's passing by. Makes total sense so far. Alright, I'm digging it. It's obscuring the sun as it passes in front of it. I'm with you. It makes total Occam's razor type of sense, right? Looks like an annular one, but that's no problem. Look at, so it's still continuing past it. Alright, that's cool. I mean, that's more or less what you would expect if things were simple and we lived on globe Earth in a system of heliocentricity. Well, it's a pretty good bonus for Stellarium. Very accurate, very good. Alright, no surprises there. But now, let's see what happens. This is a lunar eclipse that happened May 26, 2021. This is from NASA. So let's compare it with the simulation that we just saw, and hopefully everything will be the same. Okay, well, it's being occulted from the bottom left, as we can see with my arrows there. It makes sense. Right, because obviously the moon is passing from the bottom left or whatever, the sun. The moon is passing by the Earth on this side so that we can't see it. All right, and then there's the total, and then wait, hold on a second. What the hell is that? How is it coming from the other side to re-occult it? Did it take like a right-hand turn? Did it go left? What happened there? What? I'm sure it's only that one. You know? I'm sure it doesn't happen again or anything. Oh, here's one. Griffith Observatory. Okay, alright. Well, we seem to have an occulting from which direction? Left. Left to right. Alright, super easy. That means, of course, when it's finished occulting and it, finishes, it'll keep going in the same direction, left to right? All right, continuing left to right, here we go. And wait a second. Is that, how did it do that? That crafty moon, did it like tell, no, hold on. Did we change directions? Did the sky spin a bunch more when I wasn't looking? Well, it's probably two flukes. I'm sure that this is a well-known phenomenon. NASA has an explanation, I'm almost positive. So here's one in Australia, 2021. All right. Definitely coming from the bottom right. So here comes the shadow, right? Earth's shadow is right there. It's super big. Here it is. It's coming, right? I get it. I like how this one has the timeline here. It's very nice. I've been looking at a lot of eclipses online, so this is a nice treat for me. So that's a nice one. It looks like it's a total lunar. Yep. Almost totally occulted. And there's the red. So they marked it at the beginning right there. So we have the total blood moon. There it is, total red. As heliocentrists put it, it's kicking up Mars dust right now, specifically right now, only for whatever reason, to make it red. Alright, so where's the occult going to come from? Let's see. From the bottom right up, right? Right where it came from before. It wouldn't possibly be from another direction again, because that's just awkward, man. Alright, well, wait a second. Was it, wait, from the complete other side. Oh my. It occulted from the bottom right to the top left, and now it's going to de-occult, or unobscure, or finish, whatever you want to call it, from the bottom left to the top right? What in the world is happening here? That is a strangely behaving Earth shadow, huh? Well, I would have to say that I'm not sure what causes a lunar eclipse on my heliocentric world then, because there's a lot of evidence that says this is not what it's supposed to be. Or maybe it's some sort of super projection refraction that makes everything okay. I'll have to go ask NASA later. Boy, I hope. Oh, is there one more? Oh no, another one. April 4th, 2015. Okay. Alright. So we have regular occulting from the bottom left. Okay. That's typical, right? Bottom left. Nice and easy. Total lunar eclipse. Look at that big old Earth shadow. Boy. So predictable. So friendly. So mundane. Wow. Wait a second. What? Did it take a 90-degree turn again? Did it miss the off-ramp? What happened? Hold on now. It went from the bottom left, clearly from the bottom left up. And then it occulted from the other 90-degree perpendicular. I mean, what is that? What do you think is happening there, guys? Well, we know what it's not. It certainly doesn't look like a shadow from the Earth. And let's continue with some of these other examples. It looks like I may have had some here. Does this embed work? Oh, it sure does. So we have, again, looks like we already watched that one. Yep. So these are all here for anyone to see on my database. Wow. So we're not really sure what that was, but our explanation for a lunar eclipse as a geocentric would be, so they have to be opposite each other, and since they're both luminaries, right, the sun is a greater light and the moon is a lesser light. When the lesser light approaches the greater light, it passes right through the connection between the source and the source projection in the back, and that interference causes the effect we know as the eclipse and what we call the shadow. So this causes their light bodies to interact and creates the red umbra effect. And full moons happen every month, but a lunar eclipse only happens when the moon is in full phase and it crosses the ecliptic close to the node. That's pretty much lunar eclipses in a nutshell. Now we can get on over to solar eclipses. A little bit more interesting for sure. They can definitely be different types. You have the total, the annular, partial, and the hybrid. So total is what you think it is. Annular is when it doesn't quite obscure it. Partial is any combination thereof, and hybrid is any combination thereof. Sorry, partial is when it gets almost to the end, right? And hybrid is anything in between. So again, starting with the heliocentric explanation, the moon passes between the sun and the earth, completely blocking the base of the sun. In this one, actually, geocentric and heliocentric explanations are very close. We're not starkly different on what causes a solar eclipse. However, I think the method would be vastly different. So we'll go into that in just a minute. But essentially, it's the only type of eclipse where viewers can momentarily remove eclipse glasses, they say, which are not, safe when the moon is completely blocking the sun. And of course, we have one of these coming up on April 8th. I went ahead and predicted that on Twitter for everyone, just to be sure. And then we have the annular, which is a type of a solar that isn't quite completely obscured, but that's just a basic type of eclipse. Again, they happen far more commonly than you'd think. And let's go look at what an annular eclipse would look like. We could definitely take a look here. And so this is, again, looking at the sun with a nice solar filter. And here's what could only be the moon, which, by the way, is in new moon phase here. So it can't be seen. No one knows where it is. Hasn't been photographed. But here it is, obscuring the sun perfectly, right? Because what else could it be? Nah, it's clearly the moon. And then off it goes, doing its right thing. I mean, at least we know this time it's taking the right directions and not doing any abrupt right turns or anything, right? Well, that seems pretty self-explanatory. I'm on board with that. Partial, so only a part of the sun will appear to be covered, giving it the crescent shape. So let's just take a quick look over here. Looks like it's going to make it. Oh, but it didn't quite make it. So if you remember what we said about trying to guide it right here, right? So this one was a miss. There's a miss over here. This is what the system would be. So this one, oh, just barely made it over here. That's what we're talking about. Let's take a look at a hybrid. Boy, that is too long. Let's look at this one. Wow, that's a nice one. What happened there? Oh, it did a full solar. Okay, so here's the so-called moon, again, in its new phase, so invisible, and nobody has seen it. Nobody can see it approach. Right there's a beautiful effect when it just happens to hit the total. That's the sort of effect we're going to be able to see on April 8th, I believe, by the way. All right, so that definitely makes sense. I'm with you there. However, one final thing to throw out as for a solar eclipse. Really cool video I found on TikTok of a person explaining the same thing for a solar eclipse. I'm just going to let this play a little bit.
Hey friends, have you ever wondered why they tell you to never look at a solar eclipse? I'm going to tell you something that's going to blow your mind. In these images of a real solar eclipse, you're going to start to notice something. Notice the color of the eclipse portion and the color of the sky. Here's another picture. Check it out. The color of the eclipse portion compared to the color of the sky. Have you noticed something? I have. But don't be distracted by these CGI images that NASA likes to feed to you online. That's fake. And that's fake. Those aren't real images. But this one is, and this is. So you've probably noticed by now that the sun is actually invisible in the eclipse portion. That makes no sense because, wait, hold on. The sun is a ball of gas in outer space and the moon is just a dusty rock. Au contraire. The sun is actually a great light and the moon is a lesser light. And during a solar eclipse, the moon is during its new moon phase. It is devoid of light. The moon is empty. It is empty. That's why this empty portion is coinciding with the sun. And when that happens, you can see directly through the great light. You can see directly through the sun. None of these things are three-dimensional above us. They're all inside the firmament. Boom. Read the Book of Enoch for further explanation. During a new moon devoid of light, it is empty. The emptiness is inside the sun. The sun is passing through the moon during a solar eclipse.
The Book of Enoch, right, has this description of it as a lesser light, and it has been devoid of its energy by the time it's in the new moon phase. So it says, the Book of Enoch says, what happens during a solar eclipse is the moon passes right through the sun, because it's a clear body at that point and we can't see it. We can only see it when it goes through the sun, and that's what causes the red and orange hue as well when they actually make contact. This could also explain the Elias effect and electromagnetic interferences when eclipses happen. Very strange things happen for eclipses, and this is probably why when they touch each other, when the light bodies touch each other, there's some sort of effect that happens. In any case, the geocentric explanation for solar eclipses, like I said, is basically the same except for that methodology, right? Their proximity is still the cause, but the way in which they interact is vastly different, of course. Symbolically, this is where the Ouroboros comes from. It's where the dragon eats its tail. The sun really just eats the moon as it passes by. And again, something to keep in mind that every new moon is a mini eclipse, but only when they're lined up at the nodes does a total eclipse occur. And then to my favorite type of eclipse, the Selenelion. Right? It isn't really a type according to Wikipedia, but we'll allow it because we love the Selenelions. This is one from October 2014, right? And they said that both the sun and the moon are visible, even though supposedly one is shadowing, occulting the other. It says also a horizontal eclipse, and it's again when both the sun and the moon are in the same time. How is that possible, you say? It just refracts right over the edge of that ball until you need it, and then it comes right back. But the best one we have, the best quote we have about Selenelion eclipses comes from, let's see, Frederick Henry Hook, who was quoted by Samuel Rowbotham in his book, The Terrestrial Plane. And his quote is, according to the new theory, the false one, a lunar eclipse occurs when the sun and the earth and the moon are in a straight line. But it's documented that since the 15th century, more than 50 eclipses have occurred while both the sun and the moon were still visible above the horizon. In other words, the sun and the moon were visible at the same time in the sky while the moon was eclipsed. And this is the kind of thing that just gives me goosebumps. While the moon was eclipsed, for example, on July 19, 1750 in Paris, observers saw an eclipsed moon while the sun was clearly seen in the sky above the horizon. The same thing happened in the eclipse of April 20th in 1837, on September 20th in 1700, and on June 16th in 1666, on November 3rd, 1648, and July 17th, 1590. Also, a recent documented event occurred in August 16th, 1989, where the partially eclipsed moon could be seen rising while the sun was still setting. Now that means that the Earth, Sun, and Moon were not aligned as they are required to be while the lunar eclipse occurred, so therefore it is impossible that the eclipse was caused by Earth's shadow being projected onto the moon. Another thing they say is that the solar eclipse occurs when the moon stands between the Earth and the sun. So we went ahead and found that book here. I think it's just a chapter on eclipses, but we can go through and read what he was talking about. Here it is. According to the globular theory, his picture, very, very nice and accurate. He says, Aries says, oh, it's definitely refraction, when he asked him. Apparently Rowbotham was concerned, wrote into the Royal Society, but they let him know everything was alright, it was just refraction. He, of course, said, that's bull. He said if refraction did throw up the sun, then refraction would throw the shadow. Yada, yada, yada. How is this possible, essentially? Let's see here. And he just goes on to observe the eclipse cycle, and he does pay tribute to the eclipse cycle, saying that that is how people would know from ancient times when eclipses were occurring. Right? And it says eclipses occur in cycles, 18 and 10 and a third days. There you go. And of course, we said the Greeks made the use of it. You quoted Babylon because they had their Metonic, or at least an 18-year cycle. And again, just the 50 eclipses he had mentioned with his depiction on why they were impossible. And again, another part of the Selenelion eclipse is not only does the moon and the earth, does the sun and the moon appear in the same frame, but they go the opposite direction, kind of like how we saw with lunar eclipses, mysteriously, where the apparent object doing the occulting would veer off halfway through, or take a sudden turn, or for some reason occult 90 degrees as an offset. That seems weird for that super dependable Earth shadow. Here's a video when I went into the Selenelion eclipse, so we can just describe the one I think that we talked about in April. Yeah, let's go for here, because then I went into it. Pictures, and they say, hey, based on this, a lunar observation from way back, is it possible? Totally possible, don't worry about it. Refraction lifts them a bit higher, even though they're completely visible. So this is 1989, August 16th, right? So that's the one we were just talking about, and it's in Hawaii, and it says, actually, here's the sun, right? There's the eclipse. Where's the moon? On the other side, all the way over there. What? On the complete other side of the horizon. What the hell is going on there, guys? Well, definitely refraction. Let's just briefly go through how one can determine what type of an eclipse it will be, right? They use the three periodicities. As Steve told us in the beginning, they plug it into our symphony of harmony, right? If we each have a frequency, then you look and see which frequency occurred last to see what'll happen next. But essentially, what we need, there's three terms: the synodic month, draconic month, and anomalistic month. They coincide perfectly with almost each cycle, but let's see, for an eclipse to occur, the moon must be on its path in the sky that it lines up, it must be in the right phase, and it must be near the sun at this point, right? So repeat occurrences of the lunar phases result from solar and lunar orbits producing the moon's synodic period, 29.53 days. So the optical effect that we call the shadow of the Earth or the moon falls to the north or the south, depending on this one. Eclipses occur when the sun and the moon's orbital path crosses at the node. We've already been over that. With the new or full one near one of the nodes occurs, every 6 months-ish. And then they said this is Saros because they highly line up perfectly and occurring at a node. We know now it's really just when the sun and the moon intercede at the right node and the moon is in the right phase. So the anomalistic month is 27.54 days, and that's supposed to be the periodicity of the moon with respect to the lines of apex in its orbit. Essentially, all three or all these terms are going to be descriptions of the geometric path that the moon takes above the Earth, right? They're all going to be different parts of that, whether they mark it when it comes back to the node or mark it when it comes back to the sun's ecliptic, or when it makes a full rotation down to the stars. They're going to compare it to a whole bunch of things, and then they're going to use those factors to make predictions. Right, so after one Saros, the moon will have completed one whole number of synodic, draconic, and anomalistic periods. Right, so they're all different, but at the end of a solar cycle, they're all telling the same amount of time, which is crazy. Right, but that's just the way the synchronicities and periodicities will work together. So these three cycles and the harmonics between them determine when, where, and how solar and lunar eclipses occur. The source really is just a dance of natural harmony between three of the moon's orbital periods: synodic month, anomalistic month, draconic month. And again, the synodic month is just new moon to new moon. So that's right before it gets to the sun, its least energy, least luminous phase. When it comes right back to that peak phase, that will denote one synodic month. The anomalistic month, which is perigee to perigee. So it marks the point at which the moon is furthest away from the Earth, and then it marks it when it returns to that furthest away point. Super easy. Draconic month is the node to node. So remember, we have the ascending and descending nodes that cross the sun's ecliptic and travel backwards in relative to the sun and the moon. And once the moon crosses one of those, it's a draconic month when they come full back circle. Right, so again, it has the same amount of synodic, draconic, and anomalistic periods, which all equals the same 18-year length, right? So when we go down to here, we can see that each one equals about the same when it gets down to it. That's super interesting. Then that we can usually go right into the cycles of time after that, but we're not going to quite go through all of that here. We don't have enough time. We're already over an hour and a half for everything to do with eclipses. So let's just speed through these. They got the important draconic month, right? The most familiar lunar cycle is the synodic month because it governs the well-known cycle of the moon's phases. So draconic is node to node, remember, and synodic is phase, it looks like. The mean length is 29.53 days, which is just about just a little bit slower than the sun, which the speed difference is what causes the revolution and the dance and the ultimate greater cycle. So after completing one revolution with respect to the stars, the moon must continue a little further along its orbit to catch up to the same position it started from relative to the sun and the earth. So that explains why the mean synodic month is longer than the sidereal month. And according to the astronomical convention, it's always a new moon when the geometric ecliptic longitudes of the sun and moon are equal. So that's how they determine the synodic month. The relationship, they say, is quite apparent when they graph it out. And of course, I believe we have some NASA citations to look at if you'd like. This is one of their most, hold on, let's try this. One of their most used, I think, one of the most referenced sources. So let's see. Of course, this is just Fred. It's not really even NASA. So thanks, Fred. NASA doesn't do shit, right? Only Fred. So yeah, this is what we're looking at. The moon's orbit and the synodic month. This is what we're talking about. Again, this is super detailed stuff. You don't really need to know each one of these. You just need to know that the three of them are used to predict whether it's a total, partial, penumbral, lunar, or solar eclipse. This is what determines that aspect of it. And then people have done lots and lots and lots of work on this. A lot of work. And they've done, math extrapolations. They've done all sorts of work that you don't have to do, right? If you don't want to, you can just look into it. You can extrapolate the data. You can pull some data into a spreadsheet like I did, and you can just project, predict, and keep going. However, once you are able to grasp a great astronomical year with a correct dating mechanism, then you have one full unit that will repeat for all of history, and you can literally mark out all of time, which we'll get to at the very end, hopefully. Well, that'll be a good intro enough to get us started. Hope everyone is buckled in for this one. It's going to be super interesting and super relevant. All right, we can finally get into some eclipse predictions and pathways, right? So let's get going here. So let's start with here. So here's a video we put together a little while ago from an awesome channel called Revelation 13T, but pay no attention. We're going to go ahead and comment through here. So we've got the different types of eclipse cycles. The half eclipse is a 9-year. That's a SAR. That's where Saros comes from, right? So you have a SAR, a Saros, and then 325 years, a complete circle of a 18-year lunar cycle, and then 651 would be a complete circle of that. So 325 and 326 we'll talk about in a little bit. This is actually from Dimbleby's book, who's the only known chronologist that I'm aware of. He claims to have figured out all the eclipse cycles throughout all of time, going back to the time of creation, and he understands pretty much all the comparative gravy, so to speak, right? Excellent read. Without this book, I wouldn't have been able to do anything. I would have been stuck. So essentially, you got the 18-year cycle called the Saros, and you'll notice that there's that little guy over there, and he's got like an annular for a solar, lunar. He's got a little way to denote it. He knows exactly which type it'll be because that is also part of the cycle. So this is listing central eclipses, which are the biggest ones. And once they have a central eclipse, they either go north or south, depending on the node is ascending or descending. And after 18 years and 10 days, it comes back and does the same thing, except 30 degrees offset. So this would be the first time. This would be the first time that we saw a repeating pattern of eclipses. Let's see here. Yeah, so 649 over 36 period cycles. 36 times 18-year solar cycles is what it is. So 18 years times 36 in each constellation equals about, you guessed it, 641, which would be 651 years. We'll go over that a little bit later. Is the bisected it, right? So it's got down the middle, the 325 and 326 cycle. Yep. So that's always what's going to happen is you have cycles upon cycles and wheels upon wheels upon wheels. The reason that it's 649 is because he's using a different type of year. It's a 360-day prophetic year, I believe. And then, well, we're not going to get into that, but it's essentially the same. Time is a bitch to tell. So the grand eclipse cycle. it's 5 rotations of 841, 841 revolutions, and he says that finally completed on December 21st, 1843. This is the author of All Past Time, Dimbleby. What's really neat is there's always a ratio, like the golden ratio, except it's persistent in all eclipse cycles and patterns, and call it the ratio of God, or whatever you want to say, the numeric ratio. It's equidistant, always present. So 18 years is like the basic block of the cycle. It's like the building block of the cyclical nature of the sky. 18 times 2, 36. 651 divided by 36 gives you 18. Right? So back and forth we go. These are the multiples and the factorials of the eclipse cycles. Again, this is the book that we're citing. I'll have it in the description, but it's Gleason's friend, essentially, Alex Gleason's friend, and he's the only known chronologist who literally, because of eclipse cycles, has traced the history of everything that's ever happened back through creation. So definitely worth a shot. Go check that out. Again, how come we don't have any chronologists anymore? Is that a dying profession, or do we run out? Did they get stamped out? I mean, what's going on with that? And move right along. These are just the pretty much the testimonials to Dimbleby, saying how awesome and great he was and how accurate, right? Read them, and it's just like glowing reviews. I've read all your time's biggest pleasure, lifesaver, delight. They comment like it's a pleasure read, right? Like it didn't save the world or whatever. Anyway, I mean, imagine you went through all the work of lying to people and hiding their history, and then someone does something like that. Right here's the bread and review. This is the meat and potatoes of the whole cycle, right? So, what it's telling you here is the types of eclipses. The solar, partial. Solar, lunar, partial, right? And that goes in a definite order. As you can see over here, it starts with 1 and it goes all the way to 70. And so this is a 70 eclipse Saros cycle. A little bit different than how NASA does it, for sure, because they're going to do a succinct series not related to this, right? Each time they start a central eclipse, they keep it in a line. So what this is going to do... Alright, so let's go through this again. We have in depth. So we have one solar year, when years when the sun travels through each of the 12 signs of the zodiac, but it's not exact. And what happens is, as the sun goes forward through the 12 constellations at the spring equinox, the signs start shifting backwards, which is an astrological phenomenon, which in most of this we had to lean a little bit on astrological findings and research because we absolutely needed it. So when we're looking at a wheel within a wheel, right, it's spinning one way, but it's looking like it's spinning back the other way. It's an optical effect. They say it takes, that big grand cycle of 25,800 years for this to occur. I'm not buying that, but that's been the story for a long time. For the sun to be in a different zodiac and a different equinox, etc. And let's go back to the Saros cycle and let's see exactly how this is pulled in here, how they use the cycle to go from the Saros and how they map it out and how they relate to each other. Let's see here. So 360, right, times 2.5 divided by 180, which gives us the 1260 days we were looking at before. And then we can go on to look at our teams of eclipses, right? So this is going to represent a common team of 70 eclipses on average. It's a ratio. So this 37 annular, or that could be, and this total or annular, and that's the total amount for the whole cycle. So they break this down quite a lot. You get 33 partial, 37, 33, and 37 gives you 70. So basically, what we're pointing out is a natural break, another harmonious break, a division, a split, if you will, of 70 into 37 and 33. And astronomy has these splits all the time. So the first half of the 18-year Saros cycle is the eclipse cycle. It contains 33 eclipses, and the second half would contain 37. Interesting. It's almost like a mirror image, right? They always have, hey, look, a 37 is 33, 33 is 37. So we're just gonna take a look at, of the 70, what is the relationship from one to the other, and how do we know which is going to be which? Right? There's always a couple. There's more than a little bit of symbolism with the names and the numbers, and some people are into gematria and all the symbols, and I'm not going to touch any of that. Not saying that it's not valid, but let's just keep on task with just the cycles, right? So if we have, let's take a look here, another bisecting split, right? So Saros split in half, like we said, is 9. It's a SAR, that's a half a cycle, or a small cycle. And then if you do those small cycles repetitiously, you get 111.5, which is 1111 sono months, which is synodic months, which is that particular integer from the lunar periodicity, right? An eccentricity of the moon. Another interesting thing we're going to see is the types of eclipse as they go on, right? The order in which a lunar, solar, partial, annular appears is important and is trackable and is part of the cycle. So we do want to make sure that you understand every aspect of the cycle, which means from Saros to Saros, the comparisons are half cycles. So the ninth or the halfway through a Saros will compare with the next Saros, and full way through the same Saros will compare with this Saros. That's a little bit complicated, but essentially, if you are matching with yourself, it's a full cycle. Matching with a partner, half cycle, right? So if we start on October 17th, 2005, partial lunar, partial solar, all the way through. And our have an end date means that we are able to attribute real life years in dates. Before, all we had was, series 1 through 70. What would happen after 38 would be another 32. We didn't have any real way to place them contextually within our history because it's been messed with so much. We didn't know how to relate any which eclipse cycle. I know when I was first looking into this, I was like, oh, I got the pattern. I can do a whole cycle. And I was like, but which cycles? I don't know where any of them are. And that's the thing that they struggled with for a long time, until someone came along and became a chronologist and helped everyone out. So it's still in a pattern, right? We're talking about the pattern of eclipses, solar to lunar to partial to, it's all done according to the synchronicity or the harmonic frequency, as Steve put it. It's all done to a pattern. So here is a specific Saros from NASA, which we're going to be going over a lot. Spent a lot of time with NASA on their website for eclipses, or should I say Fred's website. So this is Saros 136, and we're going to go through a whole series. So what a Saros series is an eclipse, or a lunar eclipse will happen again 18 years and 10 days after every time it happens, right? Because that's the cycle. It'll be a little bit off from the place that it happened, but about that time plus 10 days, it will always happen again. So what a Saros is just a series of 18 years in between each eclipse, and it plots them together as a series, and that's what that Saros is. There's a lot more to it than that, and there's a lot more complicated things specifically, but pretty much what it is. So this one is on October 7th, 18 years and 10 or 11 days later. And then you see the 18 years from there, you bring it to October 17th, 21, 50 over here, and then you see a predictable pattern. Right? So it's kind of a predictable lunar cycle. Get a unique look at something else that'll help you understand it even more. So here is a completely detailed Saros cycle. Calling it, say, 9 of 36, but what it is remember that 36, all the way around 36 times. Eclipse repeat 36 times for a total. But that's what that's referring to, right? So this is 9 of 36. That's a real life date that got put to one of these eclipses, so we can start to attribute, the chronology of history without having to rely on man or written word or anything like that. So, looking at here, look at the grand eclipse cycle of 651 years, which contains 2,520 individual eclipses. Right, and it's fascinating. But we're looking at 651. Within the 651 years, you'll see this eclipse 36 times, right? That essentially means that it's going to pop out and go into each of these constellations. So it starts here, right, in 18 years and 10 days. And it goes here, 18 years, 10 days. Then it goes here, 18 years. Then it goes here, 18 years, 10 days. Follow me? It's super hard to understand unless you have this visual here, which is just incredible. Right, so it's just solidifying what we're talking about here. It starts here, or it starts with whatever, right? And then 18 years, 10 days, 18 years, 10 days, 18 years, 10 days, 18 years, 10 days. It helps specifically in this case to visualize it mapped out on like a Gleason's map, because that would give you a circular path, and cyclical, you'd be able to see the repetition much easier than on a stretched out Mercator's map, right? So it would be weird when it looks like that. So, you know, it starts here and then it goes all the way around Zodiac, all the way, and it takes such a long time. 36 iterations of 18 years plus 10 days. So because of that little offset, it won't be exactly 8. And that's on and on and on the cycle goes, right? So within this period, this is how many eclipses would occur. So it's divided into the 12, you know, zodiacs times 36. So higher rotation every year. This is just another way to describe what we were talking about. Here's an excellent picture to show you how it's going to look. Essentially, I did a couple other ones here. So here we go. 18, 18, 18, 18, 18, all the way across, and onward we go. All right, back to the video. Let's see. All right. So if you see it in Capricorn, right, then there's been 36 of the same eclipses on that date. They'll end up back at the same date and at the same location, and then that's called the grand eclipse cycle of 651 years. Now, that is the major building block of the celestial cycle of the sky. Right? That is the major component. If you know the details of one of these great astronomical years, you can predict anything and have predicted anything in perpetuity. Okay? The only difference is when it repeats, it moves 10 degrees either north or south as the next iteration starts. So it moves, well, we measure it according to the longitude latitude system, of course, for the WGS 84. And of course, depending on which way it goes, that will determine the precession of the rest of those eclipses. They will keep repeating almost infinity, ad infinitum, right? So as far as our vantage point is, they always say, oh, it's because the Earth is spinning, but we know it's because the heavens are spinning above us, and when they're spinning a little bit faster, the difference in the speed means that when it comes complete cycle, it's just a little bit off from where it started on the face of the Earth. Makes perfect sense. Perfect sense. So there is a little bit more to go here with the zodiacs and where it would start, but we're not going to go into that right now. We're going to go back to this all-time Dimbleby paper, which again is fantastic. It says on page 122, right? He goes over this major cycle and he tells you when the last one was completed. So this was published in the 1860s. He wrote that the last cycle completed in 1843. But right here is one of the most important slides that I've ever seen, really. It's like the Rosetta Stone eclipse cycles when you're trying to study historicity or major events, historical events, pharaohs, kings, books of old, the Bible, everything. This is what you need, right? So this is wonderful. He marked out each one of these all the way through time, and when you read the book, he uses all sorts of ways to do that. He calls it the 5 astronomical lines of time. There's solar cycles, lunar cycles, transits, actual history, and then books. Here we go. So he said that one ended right here, and that this one starts right at the end he had it on. So there's 36 eclipse cycles there. That's in a 651 cycle. That actually ends at the same point. But anyways, what we're going to show is how it goes here. So this is, he's got the last 651 cycles starting on December 27th, the year 1210, and it moves every 18 years to a new Saros, 18 plus 18 plus 18, all the way down. And then we finally get to, like, say, 1300 to 1318, so it jumps 18 years, right? That's what we're looking at. Starting eclipse, which is called ventral eclipse. The first eclipse of each Saros cycle. That's very important. The central eclipse means that it's the first in a series, and from there will determine whether the precession will go north or south, depending on whether the node it came from was in the ascending or descending. Super easy, super basic to understand. Right, so you work your way down the line until you get to this one. This is where you get 36 of them. You start all the way back at the beginning again, right? That would be, what, 18 to that year, 1842. And if we happen to pretend to do all of this extra work, then we'll finish that cycle, right? 1842 plus 18 is January. There's a huge change there. It looks like it's not 18, but it is. Now we're at 1861. So this is a new 651-year cycle. This would be cycle 1 of 36. Remember how we said the other one was 9 of 36? We said it's attributed it to being about 9 of 36. That's because we knew exactly where that would come from and how far along in its theme it was. So let's see, on January 22nd, 1879, right there, we started next Saros cycle. On the list goes 1897 to 1915 to 1933 to 1951 to 1969 to 1987 till we got to the 9th eclipse cycle, which is the 9 of the 36. That would be on April 8th, 2005. So, again, we've just completed an exercise, added the periodicity to one of these new eclipses, and we had predicted the next eclipse, right? That's actually one of the current cycles that we're still in, that's still going on today. 9 of 36. That's the big picture of all the stuff we're looking at. Because of this, we know exactly what number of eclipse cycle this is and how many more it came from, right? So, like all the way from 1 to 22 and then to 44. So, the other important thing about this, that we line them up like this, you see the relationships between each cycle that NASA would obfuscate the nature of the way that they present the data or give it to you, right? The way that they present the data is really strange. First of all, they divide it between solar and lunar eclipses. All 5,000 almanac one, 5,000 almanac and the other. When each cycle is bound to have a mixture of both, you're unable to complete any cycle with just one or the other. Well, why would they do that? Anyway, here we have two cycles laid up together, 9 and 10, and then we can see the half cycle periodicity, right? So watch what happens here. Let's start with the beginning of the cycle. 18 years later, in the year 2023, we have the same eclipse, right? Mirrored it. Went through that. That's the pattern. They just shift over 18 years plus 18 years, about 10 or 11 days. If you see a total solar or annual eclipse on October 3rd, 2005, you know damn well in 18 years and 10 days you're going to see another eclipse, but that's going to be on October 14th. Right? And if you just keep going down the list, you'll see a partial lunar on October 17th, 2005, see itself on October 28th, 2023. Then you just keep going on, and you see how they all match up. They all match up. So you can go down this way the list, and here's all the Saros 9 continued. June 1st, right? They all match up. If you didn't know this, like if we look at between 9 and 10, watch what happens with the halfway. So in 1 year, right, you know exactly what kind of eclipse. In a half year, in a SAR, like we started before, in just maybe 9 years, right? Then we can see 9 and 10, right? So right here. Here we go, right? So look at the first one, April 5th, and 9 years from that point from April 8th, 2005. You go 9 years, you're splitting it in half. Then it's 9 years, 5 days, half a Saros over SAR. And then you check it out. Get the opposite reflection. So because it was a solar, then you get a lunar. You get the opposite. You get the inverse. You get the inverse of the periodicity, right? If it's a path, then it would be the opposing apex, right? Right when you're at the furthest away. So you get opposite reflection. You see a solar, not a solar, but a lunar eclipse. And that's how the Saros cycles 9 and 10 would compare. And every cycle compares halfway like that. And if you never saw them together, you'd never know that. You never know how linked and similar they all were. You think they were all different. I gotta think that's kind of been the goal. They don't want you to know how linked they are, right? All the pattern is always right? So from the next one, you'll see partial of a total solar, then a total lunar. 17. Partial lunar, then a partial solar. Look at that. It's just like a. Right? Take a look here. You might be laughing, but there's always an antipode, right? So teams of 70 eclipses typically on average can be different, more or less. Divided into SARs, you'll have the 70 paired up in sets of 2. Remember, because when you have one, then you know instantly 18 years, 10 days from that point, you have another one. So anytime you see one, you have 2. That's how duplicity works. Remember that is parallels to the number 70 all the way through. Opposites, of course, discharging and charging of magnetism and attraction, the fundamental forces of nature. All this seems to have a eclipse cycle, which is meant for us to know how many eclipse cycles or how much time has passed, right? So 354 days would be a lunar year, and it's a little bit shorter than a solar year. And then if you look at the patterns, the first central eclipse was over there. And then you get 354 days later, brings you to March 29th. And that gives you another solar eclipse. Now this is going to be an important pattern as well, right? Check it out with the other one. On April 20th, 354 days again. Saros number 10 starts out that way. After the solar eclipse that announces the beginning of this Saros cycle, 354 days later, we get to April 8th, 2014, just as it says here, right? 354-day period. What's going on here? That's amazing, right? I don't know what it is to make, other than patterns and cyclical nature of God. He likes to use, things like the golden ratio and wonderful fractals and factorials that work wonderful things. So, now that we're taking a look at the similarities between the two cycles, we can take a look at the other cycles, right? The ones that are missing or coming or going, essentially, right? If this is a spherical lineup of the moon, how the sun is going to intersect with the moon, and sometimes when it doesn't hit exactly, it either goes far off, low, high, what have you, and those are marked to it, and they're either marked as coming, going. If it hits the outer edge and it's going to come in next time, then you know in the next couple it's going to hit the dead center total solar eclipse, for instance. But this is a nice way to show you how the teams of eclipses come and go, right? Or what determines when one makes a team doesn't, what determines what makes one type of eclipse for. So, yeah, individual eclipses are born, let's say, and they last about 12 years. So you're looking down the middle, and it's going to die out, then it's completely out, right? So this is just a way to encapsulate penumbral and numbral. Has to use, say, coming and going, but it's really just a lifetime of an individual eclipse that lasts on average 1260 to 1,260 years, and every 1,200 years one dies, comes back, or one starts up again, essentially. Somewhere else another one comes in, right? So it's really all just cyclical in nature, yin and yang, death and life, up and down, coming and going. So also parallels all over the place to these numbers. We're not going to go into that right now because we have to stay on track. We have to get through the eclipse cycle itself before we talk about all the other stuff about eclipses that everyone wants to throw in there. So it's the natural way. If someone gets up, say an eclipse of 1260 years, he reaches 1260, he moves out of the circle, essentially, right? It's just a perpetual cycle. It has limits and it has variation. So all these cycles is always a variation, just like the solar year right now. It's almost 365, but not quite, right? It's 365.24 or whatever. It's that difference that causes the other cycles of time. And when you're looking at how nature works and how God works and how these patterns tend to work, it's what allows for growth, essentially, and if that essential eccentricity, the cause of everything, seasons, everything needs change, right? So things like this for a reason. Wonderful to see that reason in effect. Just like when we have seasons, right? We need spring, summer, winter, fall. If we didn't have them, we'd all be in the same season all the time. We wouldn't have life, we wouldn't have death, things would grow, etc. What I'm getting at. Let's just take a look here. What's this? Perfect. And then we'll just let it play, I think. So mapped out the teams of eclipses is what she's going to do here, and I had it animated. So again, start up with the tropic lines. We're going to do the team of eclipse. We got one, and then we got the other one. So right away we got two. There it is. 1, 2, done. And we got a couple more. We got plotted 2 at once. That's 4. 2 over here, 2 over there. And then we're going to see at the end of this, when they rotate 20 degrees, that's the perpetual bigger macro cycle that they all are a part of. If the lunar cycle is the building block, that's what they built together. And then here's kind of a visualization of what it would do when you put them in a circle and you map them across the tree, right? Once you get this team situated, all they do is rotate and create the next giant 651-year cycle, right? It's a really interesting way to visualize what's happening, and it's decidedly against what NASA is trying to get you to see. So here's another visualization where I ran around the outside, just to show that the teams of eclipses will precess through the equinox, right? The precession is what causes the giant cycle. So if we have mapped out all of these eclipses and then move them 10 degrees to the right, we have a whole other cycle, don't we? And this is just some other visuals that I put together. Really, she made some awesome art, and we spent some time in Canva animating it to make it nice and professional, and I think this is just a really good visualization of what we're talking about. So you see how they travel together? That's an indicator of like the lunar nodes like we were talking about before. And this one is just a really cool image she made of the actual path of the moon. She put the phases of the moon in an elliptical orbit and then did like a combination of elliptical orbits all around. Now we can look at some of the other images, right? So this one I had said was key. It depicts the micro, the macro, and the grand cycles, but more importantly, it's the basics here, right? We haven't gone over the basics yet. The parts of the lunar periodicity and attributes that govern what type of eclipse will be next. As Steve had said, see if something has happened before and when it will happen again. So we have the perigee and the apogee. Those just mean the furthest point and the closest point that the moon has on its orbit. That's all that one means. And this guy did some awesome math, which we're going to go through. But it essentially just means that this is how they determine what's going to be the same solar eclipse. It's the alignment, which is the synodic month, and then it's the true alignment through the moon's node, which is the draconic month, and then the same distance between the moon and the earth, so the anomalistic month. So those are the 3 terms that we haven't dealt with yet, but they do mean essentially what type of eclipse is going to be next. So we have the synodic, meaning the alignment of the sun and the moon plane, and then you have the draconic, which is the true alignment through the moon's node, meaning that once it passes its node, the next time it passes its node will be the next year. The same distance between the moon and the sun. So if it's at point X, when it will be at point X again. That's what an anomalistic month is, right? So those 3 are not super, well, they're kind of important, but we're not going to deal with them a whole bunch, I guess is what I meant to say. They are integral in determining which eclipse is next, but so again, conditions have to be met as always. The same distance, the true alignment, and right from the ecliptic plane. So it has to be exactly where it started from to satisfy all of these, and we'll get to what that means in a second. We know what a Saros cycle is, exactly 18 years, 11 days, 8 hours. That 8 hours is what processes it a little bit further each time. Right off the NASA website, of course, the periodicity and recurrence of eclipses is governed by the Saros cycle, which is this giant 18-year, 11-day cycle. And then it goes over the natural harmony between 3 of the moon's orbital periods, or essentially those 3 integers that we had akin to hinted at earlier: synodic month, new moon to new moon, anomalistic month, perigee to perigee, or furthest to furthest, draconic month, node to node. So when it passes its node, the next time it's back at the node. So when you do a complete Saros, right, those different months actually add up to all the same amount of time, crazily enough, right? So even though they're 29.5, 27.5, 27.2, one Saros is equal to 223 synodic months, 239 anomalastic months, and 242 draconic months. So what a weird serendipity periodicity that is, right? They also equal to the same thing within a couple hours. So this is just going to go into what separates a Saros from the next Saros and why they're not identical. Like we said before, this was the main difference, that 8 hours. It says the extra third day of placement means that the Earth must rotate an additional 8 hours, or 120 degrees each cycle. Of course, for us, that means the sky must rotate an extra 120 degrees, which places it in a different spot on Earth, right? What it does, though, is it does this 3 times, so this results in the shifting of each successive path by 120 degrees westward. So a Saros series returns to about the same geographic location every 3 Saroses, or 54 years each. But there's only a certain amount of Earth to go to, right? 120 degrees, 120 degrees, 120 degrees. That's almost a third of the Earth. It displaces it by the next time, okay? And that's the same thing for all of us. And let's see what else we have. So my boy here did some math on a spreadsheet and figured out, he just did pretty much an aggregate summary of all the lunar eclipse data that they have. What about is the mean time for each one of these things? And he essentially figured it out to a heck of a function here. Let's see if we can get the results. So there we go. He took the means of all the synodic, anomalistic, and draconic months over each period for each Saros and each great cycle, and he did the mean average and figured out more or less every time it's going to be 6,585 days and 10 hours, which is about average, right? It's about average. And that's a very useful determination, though. The fact that he's able to do that was very impressive, well, to me, and I guess it's probably because it's a nerd thing. And since we mentioned it so much, we might as well talk about the spreadsheet, right? It's nothing magical, of course. I just took all of the data given from, not NASA. NASA doesn't do shit with eclipses, but from Fred and Gene and the people who actually did the work. I took their data and I exported it into Excel. I had to do a lot of OCR work to make it manipulatable and copyable. If you guys know what that means, it was not fun. And then once I got it into Excel, it came in a form much like this, right? And then I added some columns. I did some additional VLOOKUPs because I wanted some other things to be included, right? So if this is here, then I would probably do a VLOOKUP with one of these other descriptions, right? So that gets copied over. Let's see, something like this, right? VLOOKUP over there, and a couple other different columns. Essentially, I added some customs to it, and then we produced a pivot table, right, which looks a lot like this. If you know how to use pivot tables, it's not that hard. You just got to put them in an actual format. And what this does is automatically aggregates all of my data by a certain amount and by certain fields, hence pivoting, right? So I made Saros series a filter. I put it up over there. And then when we want to change things, or I want to look at things, I just have to pick a filter and see how it's going to be mirrored, right? So this one looks like it's stuck here. Let's unfreeze these. There we go. All right, so if I want catalog number, see? So usually what I do when I'm using this is just look at the dates. Like I'm going to look for, say, this one coming up in April, I would have to say equals 2024. And then here are the eclipses that happen in 2024, anywhere from 2 to 6 a year, right? And here's April's right here. Oops, didn't mean to do that. Oh, did I split screen? No. Okay, back we go. So essentially, right, if you look at any of these, one of these lines has all the data you need to actually plot anything. This is everything you need. Greatest line, central line, path width, gamma, eclipse magnitude, type of eclipse, lunation number, eclipse type back, sun azimuth, latitude, longitude, definitely need those. Cannon plate, and then a whole bunch of other stuff from the Saros cycle. So you do need most of that, and you do need especially GPS to plot anything on a map, as well as a couple other factors regarding the shadow, the penumbra, and the umbra, which we'll get to in a little bit. But I just wanted to show you the spreadsheet. It's definitely not magic, but it does help to be good with Excel. All right, now time for my favorite segment called Is It Heliocentric? There's been a heated debate online on Twitter and amongst people who think that heliocentricity can predict eclipses using things specific to heliocentric people like Newtonian mechanics, orbital mechanics, gravity, the mass of a planet, etc., etc., etc. Of course, we think that is bullshit, that you can make all eclipse predictions simply by making observations outside, taking angles, and noticing patterns. We shall see which is correct.
McToon or Google level 1 or anything doesn't really know about it, they'll be like, yeah, it's heliocentric because it uses lunar and solar ephemeruses. Like, oh yeah, it's the same thing that Walter Bisson told me, like right off the cuff, which I immediately looked into and was like, oh, this did not work out. Hold on, let me get this up. Unvarying Keplerian ellipses. Everyone familiar with those?
Oh yeah.
Okay. All right. So optical things in the sky, pathways completely devoid of mass. Got it. Cool. Then it says considered only the gravitational attraction between the sun and each planet, while keeping unvarying Keplerian eclipses. Okay, so you're doing two things. It looks like, and then it's like, okay, we were able to prove with accuracy, but how much did they improve? You say? How much was all this worth? How much is it exclusive to heliocentrism? Well, 0.00001 arcsecond and also 0.0005 arcsecond in longitude. So negligible, in fact, that like if a butterfly farted in the wind, the whole thing would be off. They don't even bother applying it because the lunar limb variation by itself is throwing that way to hell. Literally, they concluded, hey, we did a lot of work and a bunch of calculations, and it doesn't mean dick. We decided not to use it. Good luck. Oh. So wait, what was exclusive about this not... hold on. Am I missing something? Hold on. So this one is basis on increased periodic terms. So what they did was 37,862 extra terms for the moon's longitude, 77,000 for the latitude. Literally, they just added a bunch of cycles to it to see how accurate they would get, because obviously the more you're off, the quicker you'll see it. But if you're off a little bit, it'll show up after a long while, right? And it'll show up in giant exponential numbers. But then it says, oh look, again, we did a lot of work and it has no practical impact on the present work. Okay, cool. So it didn't use it, doesn't matter. Again, okay, all right, it's super exclusive. I'm definitely feeling comfortable with my heliocentric proof at this point, right? I'm gonna go tell other people to look here, I think. But then like, oh, actually, what you need is a geocentric ephemeris, because everything is geocentric. So like every time you have to go look at an ephemeris, it's like, well, we have the geocentric ephemeris. Like, hold on, I thought that we were trying to prove heliocentric. Well, one of those is from a satellite near Jupiter. Oh, okay, and we determined that because, oh right, we didn't, because it's on an ECI frame, which is self-corrected for. Oh fuck me, right? Like this is so ridiculous. That's proof of anything that I'm like, all right, that's dumb. The next thing though, right, is they always say the shadow. You definitely can't predict a shadow, which was like on Twitter the first thing I did just to be a dickhead because I knew they were gonna do that. However, it is kind of hard. Like the way that they had to do it was some monk made an observation of a shadow of some eclipse that he then used to astutely like modify the eclipse prediction to see like, well, the next cycle it's going to be like this much this way or whatever. He made an observation of a shadow that was an optical like radii, and then he increased another predicament by an amount of Earth's radii. So these are all optical bullshit measurements, right? So let's see. But my shadow, I think I called it. All right, so the thing that is hard though is the actual like drawing of the shadow. But of course, the thing about Excel is you only got to do a thing once to do it like forever. And even though that was really hard, it still got done. So you can just endlessly compute Besselian elements because I'm a G. But actually, what you have to do is you take this radial of like a penumbral, right? And you take this coordinate system with an L2 and L1, which you're going to use Cartesian. You're going to put yourself at the center of a celestial sphere. Hey, we like those a lot. We know what's going on with that. And then you're going to predict declination and up the angle based in units of astral units of Earth's supposed radius. And then that's going to draw the shadow. And I mean, boy, is that heliocentric or what? A celestial sphere, like by definition and by use and by practicality, is literally a geocentric. Like, cannot be anything else. So I'm confused again as to the proof for the heliocentric portion. Anyway, I think I'm good.
But awesome. Great job.
All right, and let's talk about the shadow. Let's talk about the Besselian elements and or the ability to project penumbra and umbra that everyone says can't possibly be done by anyone but a heliocentrist. So let's take a look. So if you don't know, obviously there was some issues on Twitter. People are being dumb, so I decided to pretend to predict everything, right? They were like, no, only heliocentrism can predict things. And I was like, nobody predicts anything. It's a post-diction. And they went, I'm retarded and don't know anything. And I went, okay, here's what I'm going to do. I'm going to put a wizard hat on. I'm going to pretend to do magic to predict eclipses. And until one of you does the same thing, I'm going to lord all over you. So that's what we're doing. That's where we're at. Of course, be an adult and own the kinematic and dynamic equivalence between heliocentric and geocentric positions like an adult, or, you get clowned on. So, moving right along, we figured out how to do this from a geocentric perspective, just to spite people on Twitter, but ended up putting more effort into anything than we've ever done before. So, Besselian elements essentially are just these components in the form of a matrix that you can do some complicated math with to predict essentially where the shadow will be on a map using GPS and any celestial coordinate projection map, right? Again, this is what we put on Twitter, and they said I plagiarized the definition from NASA. Of course, right below there is what I cited, where I got the definition from NASA. That doesn't help anyone knowing the definition. You can't plagiarize that. I used that to calculate the Besselian elements for the specific eclipse, of course, but no one says anything about that. So then when we're trying to essentially look at what we're going to calculate, right? Again, look it up on Wikipedia. Local circumstances of occultations for an observer on Earth. Exactly what we're looking for. But look over here. It says specifically, chosen plane, the fundamental plane. That would be what? All right. Of course. This is geocentric. Geocentric normal plane of the shadow axis. In other words, it is a plane through the Earth's center that is perpendicular to the line through the centers of the occulting and occulted bodies. Essentially, a personal celestial sphere that you could be anywhere on an Earth-centered reference frame, because there is no other way to do it. People who tell me I can't do it, heliocentrists actually cannot do this without employing geocentric coordinates. So figure that out. Anyway, what you need is those elements right here. It ends up being like a matrix. You get a X, Y, D, L1, L2, and I think U, right? And between those elements, you can just predict and project that shadow anywhere from any coordinate system on any map. And so here's just an Excel formula. Essentially, why do anything yourself when you can Google it and have someone who can write a Python script and who already did it for free? And or a VBA code or an Excel formula or whatever your flavor is of automation and efficiency. So again, I just posted the Excel output essentially. Of course, the celestial sphere is geocentric inherently, cannot be any other way. That's just by definition how it works, right? Centered on the Earth or observer. And again, when you're using coordinates, spherical coordinates, where are we going here? Oh, yeah. So let's see. Placed on the celestial sphere are analogous to the geographic coordinate system used on the surface of Earth. They differ in the fundamental plane, but of still geocentric, observer focused. Has to be. Can't be any other way. So you just put yourself in the celestial sphere and you get ready to project some shadows. So again, here's just a summary page where I was looking up of all the things that we're going to be building. This is my nice moving personal celestial sphere model. Here's just the personal celestial sphere with the Besselian elements overlay. Here's the final result my actual prediction up top from the spreadsheet that I showed them, the absolute data that was computed, the Excel sheet that we used to get it, and the resultant beautiful shadow that we were able to project using math, and nothing to do with heliocentricity, no gravity, no mass of planets, no none of that, right? Don't forget. So here's the actual one with the actual, this is pretty much an infographic, right? The celestial coordinates right up here. And we have my spreadsheet over there, and of course the final over here. And there we go. So essentially, right, this is a quick 3 to 5 minute TLDR of something fairly complicated that you don't know, you have to know how to do. You just have to know how to find someone who can program it for you, and then you can do it infinitely. And here's a nice, essentially a plot, right? If you put yourself in a celestial sphere, to get these, you just rotate it around. Literally shove a fundamental plane through that bitch and rotate it around any axis, the shadows will form. Actually kind of amazing. Kind of proud of myself. Well, that's going to do it for this episode. And man, this has not been the longest, most effort-induced video I've ever put out or ever done. I don't know what it is, but I think it'll be worth it. I think it's going to lead to a lot of crazy uncovering and deciphering and some truth that we desperately need. So thanks everyone for hanging in there for the super, super long presentation, and hopefully we'll see you next time. Well, this is supposed to be like the epic finale of the end of the project for the eclipses, that once you figure out the eclipse cycle and the grand astronomical cycle and the giant celestial cycle in the sky, then you can actually trace back through all of history how many, eclipses there have been, how many sunrises there have been. You literally can track, history all the way through the history of the pharaohs, the kings, the old from the Bible. You go absolutely nuts. And this guy, Dimbleby, was like the world's most efficient chronologist, I don't even know, and he did all of this. So he literally has the biggest book on all of these periodicities, and it is by far the most influential book that I think we've ever come across. And in it, I think you'll find everything that you need to unravel really the history that has been occulted, and the years have been added, subtracted, changed, etc. And this is the way to unwind them, right? Once you figure this out and you can group 651 year astronomical year periods, you get this, right? You get to map out how many have there been. In Gleason's time, it was about 5861, which was 1861, which would put us firmly right in the 6th, 7th, 8th, 9th astronomical age, meaning that we've only been here doing this for 6,000 years, just about 6,000 years, which is crazy if you haven't thought about it before, and if you believed in evolution and carbon dating and all that stuff. But honestly, it makes sense to me because
this Bible from 1813 has something very interesting. It is a facts page that contains a list of people and events in chronological order. It says, whereupon we reckon that from Adam unto Christ are 3,947 years, 6 months and 10 days. And from the birth of Christ to this present year is 1814 years. Then the whole sum and number of years, from the beginning of the world unto this present year is 5,788, 6 months, and the said odd 10 days. In the year 1814 the world really was 5,788 years old. This year, 2022, the Earth would be approximately 5,998 years old.
All the things that they do to try to convince you that it's longer. Carbon dating, dinosaurs, evolution, all of that needs slow, gradual change, or it's not feasible scientifically at all. So, how do they get slow, gradual change when we've only had a couple thousand years? Well, you invent it, right? No, we've been here 10,000, 10,100, a million years. Anyway, that's pretty much what I think happened, and I think that this is a valid year. I think that it's been corroborated elsewhere. Now, The other part of the end result of this wonderful process of figuring out the eclipse cycle is that there's more work to do. There's an entire series of Chronology by Kinko, I think is the name, who literally used the eclipse cycle, went all over the world, analyzed history, compared it chronologically, found all of the holes. Super interesting. I'll put his stuff up at the end here. His 5 books are in the archive that I put for my sources from EtherCause file share. So if you want to grab that, they are hard to find actually for sure. So they are all in that raw file. And man, I wish I had more time to go into the Dimbleby part and the time and the teams of eclipses and how you can unwind a great astronomical year. But I will do that next time, I guess, because this is already the longest video we've ever made. So one more time, thanks everyone. Take care.